But the work I'm going to talk about today was, it was the final chapter of my PhD thesis. So it was a collaborative effort between myself and my PhD supervisors. So that's Glenn Martin, Matt Sperrin and Niels Peak, but also with Simon, who provided some really helpful kind of clinical insights, as well as information on the data and access to the data. So yeah, I guess I'll jump in. So I'm talking about harnessing informative patterns of EGFR observation for improved prediction of key outcomes in kidney disease. And I'll talk a bit more about what that means in a second. So just a brief outline of what I'm going to talk about today. I'll start off with some background and motivations, talk about some of the key challenges that we're trying to address in this work, but also in my PhD more broadly. I'll introduce a couple of definitions that are quite pivotal to the work. I'll then delve into some methods, so the data sources, the outcomes, as well as introducing a kind of methodological framework that we use to apply to this problem. And then I'll finish up with some results, conclusions, and next steps. So I guess the motivation behind this piece of work and behind my PhD more generally is really the fact that it's becoming increasingly common to use routinely collected health data for secondary analysis of in health research studies. So it poses a number of opportunities. I'm mostly talking about electronic health record data here, but it poses a number of opportunities in that we can achieve really quite large sample sizes, long-term follow-up and quite intense monitoring without having to actually go and prospectively collect that data, which, as we know, can be costly and time-consuming. So it's a really exciting resource to use, but there are various challenges associated with the secondary analysis of data like this. And one of the main challenges that I'm looking at stems from the fact that it's not data that's collected with a research agenda in mind. Instead, it actually happens opportunistically. So people only have data recorded in their health record when they actually engage with health services. So in periods of ill health, they'll have more intense periods of observation, or likewise, when they're fairly stable, we might not see anything for years at a time. And this is what we mean by kind of informative observation. So as a bit of background to introduce informative observation, it's useful to first define the observation process, which I'm going to talk about quite a bit. By observation process, I basically mean the longitudinal way that we've observed someone over time. So like not the actual results of their tests, but the intensity of monitoring, the frequency of monitoring, all that kind of information is captured within this observation process. And as I've sort of started to touch on, these observation processes are very often informative with respect to patient condition when we're using routinely collected health data, or electronic health record data. And I've tried to kind of illustrate this in the plot on the left of this slide. So what we're looking at here are two patient trajectories. This is real data pulled out of a critical care data set. We're looking at two patient trajectories of blood glucose. So patient one is this kind of green line, patient two is this brown line. And what we can see is that patient one was observed quite intensely throughout their admission, and they were also quite unstable. Their blood glucose was quite unstable. It kind of evened out towards the end, whereas patient two was relatively stable and observed far less frequently. So patient one actually died at the end of their admission, and patient two was discharged safely. So hopefully we can start to see that the way in which these people were observed was not only informative about what we observed, so the blood glucose measures themselves, but also about what happened in the future, so about their prognosis and their risk towards the end of that admission. So this notion of informative observation, it really again poses kind of both challenges and opportunities to the secondary analysis of electronic health record data. It's a challenge because if we don't think about it carefully, it can introduce some really unexpected results and introduce biases into our analysis. But I kind of like to see it as an opportunity in that we can actually start to draw additional information about patient condition that isn't explicitly recorded elsewhere in the record. So my work is all about informative observation in the context of clinical prediction modelling. So I'm sure we're all aware, but just so we're all on the same page, what I mean by a clinical prediction model is essentially a mathematical tool that takes a series of inputs. So this is patient information. It can be demographics, like age, gender. It can be lab test derived results, blood tests like lipid markers, blood glucose. It can be medications, diagnoses, pretty much anything. We then take that information and apply some kind of prediction algorithm. So in this case, we're looking at kind of statistically grounded models, but it could be something a bit flashier like a neural network or forest-based methods. But the end output is really a predicted risk. So here we could be talking about a diagnostic risk. So that's the risk that someone currently has, some condition of interest. But here we're actually focusing on prognostic risk. So based on what we know about somebody right now, what is likely to happen to them in the future? And can we assign a kind of probability to that? And that's what we mean by clinical prediction models. So a nice example of a well-used, well-validated clinical prediction model is the kidney failure risk equation. So this is a model that has been developed to predict 2- and 5-year risk of kidney failure within patients with existing chronic kidney disease. It's been validated in numerous sort of global populations, and it's my understanding that it is quite well used in clinical practice as well. So the main form of it is relatively straightforward. It just takes 4 inputs, so age, sex, EGFR, which is a measure of how well the kidneys are filtering, and kind of kidney function more generally, and then UACR as well, which is another marker of kidney health. So it takes these 4 inputs, and then the estimated risks from the model can be used to plan for referral to other services, but also for interventions like renal replacement therapy. So although it's quite well used, it does have various limitations, the KFRE. I think one of the main ones being that it only takes a sort of cross-sectional snapshot of a patient's information. And that's true of most clinical prediction models that are used in practice. But really that kind of, it is not very realistic in terms of, in the absence of such a model, care providers are much more likely to consider the long-term evolution of these markers, especially of kidney markers like EGFR and UACR. They're looking for how quickly they're declining or how quickly they're changing over time. And these models aren't really able to capture that information. But kind of going above and beyond that, it's also highly likely that the measurement times themselves of things like EGFR are informative and might be able to tell us something about future risk. So really in this work, what we're trying to do, we've got 2 main aims. The first of which is to extend the kidney failure risk equation to allow for repeated measurements of key kidney markers, so that's EGFR and UACR, and allow that sort of longitudinal progression to inform estimates of risk of both kidney failure and death. Again, sort of on top of that, what we really want to do is see if we can improve the performance of this model by allowing it to learn from the informative nature of the way that EGFR has been observed over time. And we look at a number of different ways of doing that. So moving on to some methodology and some data. So we were kindly provided with access to some data that's held within the Grampian Dash. The data contains all lab tests that were recorded in the Grampian region between 2009 and 14. It covers both primary and secondary care, so it's quite rich information. So for the purpose of this analysis, we extracted information on, I guess, the 4 key predictors that form the basis of the kidney failure risk equation. So that's age, gender, UACR and EGFR. And we had repeated measurements of EGFR and UACR as well. We then also recorded information on 2 key outcomes. So that's kidney failure, which was defined by, it's kind of a composite outcome of a number of things that could have happened, partly based on EGFR, but also based on commencement of renal replacement therapy or transplant as well. And then we also want to know about dates of death where available, because death is quite a key competing risk for kidney failure. And we actually found that it happens to a lot more people than kidney failure itself. So we had to account for that in analysis as well. We restricted our cohort to only people with kidney disease stage 3 or 4, and that was defined by a sustained drop in EGFR of less than 60 for at least 90 days. And just to say, we tried to sort of tease out the incident versus prevalent cases here by having a burn-in period in the data. We basically didn't allow anyone to be included if they presented within the first 2 years, so that we could be at least fairly confident that all of the people were presenting for the first time with kidney disease. We wanted to capture them at that first presentation. So I guess what we're talking about here is really what I refer to as dynamic prediction. And by dynamic prediction, I mean that we're using longitudinal information to make a risk prediction, but we're also updating as new information becomes available. And I suppose there are 2 main methods that really dominate the literature in allowing us to do this, and they're landmarking and joint modelling. So I've opted for a landmarking approach because it tends to be a bit more flexible. It's also a little bit more computationally feasible than joint modelling. But the general sort of landmarking framework looks a little bit like this. So if we imagine that we've basically got a set of what we call landmark times, or these like TLM kind of times, and we want to make a prediction at each of these times. That's denoted by this dashed vertical line on the plot. At each of these times, we define a risk set. So this is the set of patients that are still at risk at that time. And timescale here is the time since CKD presentation. So it starts at time 0 for everyone. So within those risk sets, we then want to essentially make predictions using only information that has been observed prior to the landmark time. So in this case, we've got these sort of longitudinal EGFR measures. I've also put these arrows on here to denote the fact that we're also interested in the frequency of measurements, or the time between measurements as well. And then because we have these sort of multiple landmark times, we can update information, we can update the predictions as new information becomes available and continue to make these risk predictions here. The typical landmarking framework actually fits separate prediction models at each landmark time, but that's a little bit inefficient. So we took what's called a kind of super landmarking approach, where you stack the individual like landmark data sets together and fit a single model across them. And I'll go into a bit more detail about the models and mathematical details of that in a second. So to kind of summarize the approach that we're taking, I like to call it sort of two-stage landmarking. We're in the realm of dynamic prediction here, where we're updating predictions as new information becomes available, but also using the longitudinal trajectory of how key markers have changed. So to do that in a two-stage landmarking approach, we first define our set of landmark times. So in this case, that was from 0 to 1.5 years and split up. There was a landmark time every 3 months. We then define these sort of landmark risk sets, which is the people that are still at risk at that time. So these people haven't yet had kidney failure, they've not yet been censored, and they are still alive. At these landmark times, we then actually want to estimate what we think eGFR is at that time. And then we finally have a sort of separate model. So the second stage is the actual prediction model, which predicts the risk of kidney failure or death based on our observed values of eGFR and other markers. So for my non-data science colleagues, just bear with me a second while I run through some sort of notation and mathematical details. But let's assume that we have, I guess, Y captures the information on eGFR for patient I, and we have a number of repeated measures measured at times t. We then have a set of information that doesn't vary over time. So this is the ZI here. And in this case, that would be age at the CKD presentation and gender. We then have denoted this kind of WI term, which is essentially, it's a summary, I guess, of the longitudinally observed information on eGFR and UACR. So in most cases, that would be what we predict it to be at the landmark time. In other cases, it might be the last observation carried forward. And we also include in that the kind of the rate of decline of eGFR as well. We then sort of denote the information on survival time in a fairly standard time to event sort of way, where we have time of kidney failure, death or censoring. That's our follow-up time is T. And then we have an indicator associated with that, which tells us what actually happened. So it's 0 if they were censored, 1 if they had kidney failure, and 2 if they died at the end of their period. So to sort of summarize, again, this two-stage landmarking approach. So the two stages are basically two separate models that we fit to the data. So the first model is a mixed effects model that we fit to the longitudinal repeated eGFR measures. And that looks a little bit like this. So we have this G of T to effect, which is essentially a possibly non-linear effect of time. We actually found that the eGFR measures, they tend to be quite noisy, they tend to be quite non-linear. So we adopted a natural cubic spline to model that effect. We then have our time invariant predictors, location and gender. Sorry, not location, gender and age. Location is also in there because we expect some difference in the eGFR values between primary and secondary care. So we wanted to capture that with a sort of time varying factor. We then have these random effects. So these are random coefficients that should have been marked on here. Sorry. We have a random intercept and a random kind of time effect for each patient as well. And so this is restricted to just observations that are observed prior to the landmark time. So the landmarking framework says that you should never use information from the future in your model fitting or prediction process, which it sounds kind of arbitrary, or it sounds obvious, but a lot of model fitting processes do kind of unintentionally do that. So to get around that, what we do is we fit a separate version of this model for each landmark time. And so we end up with, I think it was 7 different mixed effects models. So that's the first stage of the two-stage landmarking approach. So the second stage is our time to event model. So this is the model which is actually what we use to make risk estimates. So this is what we use to predict the risk of kidney failure or the risk of death within, it was 2 years in this case. So it's a fairly standard sort of Cox proportional hazards model. We have a separate model for each outcome. So one for kidney failure and one for death. So we would actually have 2 of these in practice. And again, we have this ZI, which captures the time invariant information. We have WI, which captures the longitudinal information on eGFR and UACR. And then we've got this additional term, this row term. So this is, I've not introduced that yet, but that's kind of the whole premise of this work, I guess. So that's how we capture information on the observation process, essentially. That's how we allow this model and these risk estimates to learn from the way that we've been observing eGFR over time. And we do that in a number of ways. We sort of define and parameterize this row term in a number of ways. So we start with, you can kind of ignore the right-hand column if hopefully the wordy explanations of what these mean are a bit more helpful. But we essentially fit 8 different models throughout this process. So there's the 2 null models, the last observation carried forward approach, and then this 2-stage landmarking approach that I've just described. So neither of these models, 1A and 1B, actually learn from informative observation in any way. They're just sort of used as a comparator to see what the effect of doing so is. We then have models 2 to 4. So models 2A and 2B, all we do is we just count the number of times we've observed EGFR over the past year and use that as a predictor in our model. So in our prediction model for time to kidney failure or death, we use a separate predictor that just counts, a rolling count of how many times we've observed EGFR. So model 2B is the same, but it's just focusing on the inpatient observation. So we can often attribute risk to how many times people have been sort of in and out of hospital over time. So we thought we'd focus on that as a separate option. The models 3A and 3B are where we start to get a little bit more complex. So there's some literature in, I guess, in the joint modelling world that suggests that you can actually model the times between observations. That's quite a nice way to handle informative observation. So that's what we're trying to do here. We actually fit a kind of survival type recurrent events model to the times between EGFR measurements. And from that, we can estimate this W term, which is it's essentially a random effect or a frailty term. And then we use that as a predictor in the time to event models for kidney failure and for death. 3B is the same process, but we only use data from the last year. So that's just for comparability with the count models. And then finally, models 4A and 4B. This is where we start looking at, I guess, the variability. So what we were trying to get here was if someone's gone through a really intense period of observation and then more sort of stable or less intense period, we want to somehow pick up on that because it obviously means there was like a period of intense concern from the clinician. So one way to start to capture that is to look at if there's large variability in the gap times, then we might start to pick up on those people that have sort of dipped in and out of intense monitoring. And then so 4B is just combining that sort of variance parameter with the count. So that's all for the maths now. So you can relax and breathe a little bit. So just to summarize the way that we actually make predictions for new individuals. At the first step, we obtain our predicted or observed value of EGFR and UACR. So that's from the first model, the mixed effects model that I presented. You can get estimates of the random effects for what that would be for new people. You also estimated the time varying rate of change. So that's this point here. We want to make a guess as to what EGFR is at the time that we're making a prediction. We then estimate the frailty term, or we sort of count the number of observations. So that's this information here and the stuff I was going through on the last slide. We sort of collect that information on the observation process. Once we've gathered those 2 pieces of information, we put them into our fitted time to event model. So in the actual prediction model for kidney failure and for death, we slot those 2 bits of information into that, and then we can actually predict, okay, well, what is the risk of kidney failure and death within the next 2 years? So once we have our predictions, we want to assess, how good are they, essentially, how sensible are they, and which of these models is doing the best job. So we measured that based on three main metrics, I guess. So the first of which is the C statistic. So the C statistic is just a measure of discrimination. It tells us how well the model can tell apart patients that do and don't experience either kidney failure or death. The Braille score is a measure of sort of overall model fit or mean squared error, if you like, that's been adapted for survival models that factors in censoring and stuff like that. And then finally, we wanted to have a look at calibration as well. So calibration tells us, I guess, how sensible are the predictions that we have and how closely do they match reality. And we captured that using the calibration slope. So in this case, all of the performance metrics were estimated using a bootstrapping internal validation, where we draw a sample the same size as the original cohort from that data, but that's drawn with replacement. So people can occur multiple times in the bootstrap sample. We extract all of the data from those patients, and we fit the models in the bootstrap sample. We then apply them to the original data and estimate performance in that original data. And we sort of summarize across, I think it was 200 bootstrap samples that we used here. Onto some results. So we had a total of 8,000 patients included in our cohort, and they contributed a total of 184,000 repeated measures of EGFR. So it was quite intense follow-up and monitoring within this cohort. Only 59 of them actually progressed to kidney failure during the follow-up time that we had available, but just over 1,200 of them died. So we've just got some Kaplan-Meier plots here, I guess. So just a note, I have actually edited the y-axis on the kidney failure plot because there were so few events. It was just a straight line if you kept it on the 0 to 1 scale. So I sort of restricted that so we can actually see what's going on a bit better. So I wanted to use this, I guess, this data and piece of work as an opportunity to find a way to kind of visualize these observation processes and how they relate to the outcomes that we're studying. So this is what I came up with. So what we're looking at here are the 3 plots are each, I guess, a random sample of 20 patients that experienced each outcome. So the top plot here, these are all patients that progressed to kidney failure. The second plot are all patients that died. And then the third plot are all patients that were censored. And then the marks, the sort of circles, are the times of observation of EGFR. So the green ones are the community or GP measures, and then the pink ones are the inpatient measures. So it's quite striking, really. I guess you can see, at least in the top plot, there's definitely quite intense periods of observation, at least right up in the run up to someone's kidneys failing, which I suppose it's quite reassuring in many ways that if your kidneys are about to fail, then someone is keeping quite a close eye on your kidneys. And then even in the death plot, there seem to be, considerably more inpatient observations compared to the censored group, at least. So this can just start to give us a little bit of information on, how if this observation process can be informative with respect to our outcomes. So onto the actual model performance. So there's quite a lot going on in this plot on the right, so I'll just sort of talk through it. What we're looking at here is the 3 performance metrics that I mentioned, so the C statistic, the Breyer score, and the calibration slope. And they're each summarized separately for the 2 outcomes, so for kidney failure and for death. So if we start on the left-hand column, the kidney failure column, unfortunately, there's not really any difference between any of these lines. So sorry, each coloured line is a different model, so a different way of accounting for informative observation. And we've included the null models in there as well that don't do that at all for comparison. So there's not really any difference between any of the models in the kidney failure outcome, but we do observe pretty high discrimination anyway. A C statistic of about 0.95, 0.96 is fairly high, so perhaps there's just not much scope to really improve on that for this outcome. If we look at the predictions for death, though, or the metrics for death, so on the C statistic plot, we've got this sort of grouping of lines above this other one. So this lower set of lines, these are the null models, essentially. So these are the ones that don't account for informative observation anyway. But all of this higher group are models that have been allowed to learn from that observation process. And there does seem to be a considerable jump up in the discrimination of those models that learn from informative observation. We see the same effect in the Breyer score as well, a little bit less pronounced. But again, sort of the purple and the green lines are the null models, and then all of these other ones are ones that have learned from informative observation. The calibration, unfortunately, pretty much all of the models that I fit were quite poorly calibrated. So I think that does need a little more investigation. There was quite a lot of variability in that across the bootstrap samples as well. But there were no at least significant differences really, because they were so variable. There seems to be a little bit of improvement from this frailty model for the outcome of death at least. But yeah, there's not too much going on there. So to kind of summarize what we found with these sort of model performance metrics, at least, it seems as though informative observation can be harnessed for predictive benefit, at least in the prediction of death in chronic kidney disease patients. Unfortunately, a lot of the variability in kidney failure is already really explained by the model predictors that go into that model. So if we think about it, we're trying to predict kidney function from we're trying to predict kidney failure from existing kidney function, and it's not surprising that that's already a really strong predictor, and we've already explained much of the variability, whereas that's not really true for the outcome of death. But there's less, it seems like there's less scope or less room for improvement really with the prediction of the kidney failure outcome. Another thing we saw is that so the simple models, they're just counting the number of observations, they didn't really offer any improvement over the sort of more complex frailty-based parameterizations, which I think it's quite a reassuring finding in many ways. It's always nice if we can do something simple, then we absolutely should start with that. And I guess that would be my recommendation in other areas. Obviously, that might not be true in other clinical exemplars, but it certainly seems to be the case here. So in terms of next steps, I'd really like to run some more, I guess, sensitivity analyses on this. I'm wondering if some of the improvements in the prediction of death are down to the fact that we're actually capturing people with other comorbidities. So if you think, you know, people with like cancer, diabetes, or even heart disease, they're more likely to be like engaging with healthcare services more frequently. So it might just be that we're sort of capturing that information as a proxy via this observation process. So I'd like to run a sort of sensitivity analysis to check that by incorporating those conditions into the model itself and see if the same results remain. I'd also like to look at some kind of clinical utility and decision curve analysis, because they're fairly moderate improvements that we're seeing at this stage. So it'd be really helpful to see what impact those improvements actually have on the decision-making process, if any. So, you know, the decisions that are made off the back of these risk predictions, do they change at all based on these sort of new models that learn from informative observation? And finally, I'd like to look at some external validation. So do the same results still hold in global data sets? I think one of my kind of concerns with some of these models is that the way that we observe patients might not be consistent across different settings, across different populations, and that could start to put these models at risk of really degrading once they're implemented somewhere new. So it'd be really useful to check that in new places, new settings. It might be nice to sort of look at this in a setting where we had more kidney failure events as well, because we had very few. I'm not sure if it would change anything, but I feel like we've not really had much of a chance to look at that properly. We're given such a small number of events. Yeah, so that kind of summarizes where I'd like to take this work next, and that's it. So some references, people that I've drawn on, and a little bit of shameless self-promotion here as well. we published a review article on these sorts of methods and topics a couple of years ago, and all of the other references are people whose work that I've drawn on in this project.